You don't think she was smelling my Cupid thing and got a confused? I love it, but then also they're like that
Yeah, I thought that was so efficient. It's so cool.
Oh, yeah.
Scroll down. Yeah, it was. But it just rows. There's Really follow question one before. Yeah, or five. We were thinking about that later.
What's that like? You might have questions. I saw it. And then like a few weeks later, she was like that. Yeah, that's definitely my time. I saw on the ground. That's like so.
I'll let you know.
That's a tragedy.
Yeah.
Really, really cool.
Okay. So, assuming that you all at least listen to the base network specification stuff, I will repeat part of it today, mostly to check whether you got it, because it's important that you understand the basics. So it sort of works as a kind of an extra review kind of a thing. I won't repeat exactly what you saw, but I will ask related questions, and I'll also take any of your questions. Before I start, are there any questions? Okay, so you should understand this side by now. So you need to understand that the topology of the base network implicitly specifies conditional independence assertions, and that a node is independent of its ancestors given its immediate parents, and the numbers at each node specify the conditional probability table of that node being true or false given a configuration of values to its parents. We are looking specifically at the Boolean variables right now, but in general, the idea of base networks is general. So it can be for multi-valued variables as well as continuous variables. In the case of continuous variables, in the kind of multi-valued variables, you can still have CPTs. In the case of continuous variables, you can't actually provide CPTs. You have to provide some analytic expression, such as Gaussian distribution or some exponential family distribution and so on. We won't get into that much, but it's just worth keeping in mind. And so the numbers specify the conditional probability tables. Given both the topology, given the topology, you know how many numbers are needed. Once you figure out those numbers by either asking experts or by analyzing data and computing what these probabilities would be, assessing what probabilities would be. So the so-called Bayes net learning, which we will talk about, or statistical learning, is essentially learning the topology and learning the numbers behind a Bayes network. That's it. So if I give you a whole bunch of variables and I don't tell you anything else, then you need to kind of first decide what topology, and then decide, given the topology, what should be the numbers. And it turns out that of those, we'll see when we get to that in a couple of classes, that if somebody gives the topology, learning the numbers is actually easy. And if they don't give the topology, then it becomes a repetitive task of guessing a topology, learning the numbers, getting another topology, learning the numbers. And the different topologies of Bayes networks are roughly like, given a bunch of points that you're trying to fit a curve to, should you fit a straight line? Should you fit a quadratic? Should you fit a cubic, etc.? You see what I'm saying? There are very interesting corollaries. We'll get to the connections there. We'll get to that. So once we get the numbers and the topologies, the Bayes network uniquely specifies a joint distribution over the variables. It has to be clear to you. And if you're not, this is a good day to ask that given a joint distribution, all you ever needed, in the case of logic, all you ever needed is essentially the truth table. In the case of Bayes networks, all you ever will need in the maximum is the joint probability distribution, which is truth table, and for each the world, you give a number, which is the probability that that world is likely. And then a particular fact that holds in K of those worlds essentially captures the probability mass associated with all those K worlds. Do you understand what I'm saying? Okay, that's how you start talking about probabilities. Okay, so you should know that if you know the joint distribution, then pretty much any query, any probabilistic query can be answered. So what are the kinds of probabilistic queries? So if you have, let's say, A, B, C, D as the variables, you might ask, what is the probability A, B, C, D, which will be a specific entry in the joint distribution table. Or probability A, which will mean you need to take all the rows in the joint distribution where A is true, add those numbers up. Okay, or probability A given B, which is, first let's say probability A and B. What is probability A and B? You consider all the rows where A and B are both true, and then add up the probabilities. Probability A given B is probability A and B by probability B. Do you understand what I'm saying? So actually, you can answer pretty much any of the queries related to a set of variables if you know the joint distribution. You don't normally need the full joint distribution. Remember, in the logic, we know that if we have the full truth table, we can answer a query, any entailment query. But the whole proof theory that we described, which is like doing resolution or doing mod exponents, which are these inferences, those would short circuit from having to compute the entire joint distribution, entire truth table, model theoretic entailment. Okay, so that was something that we could do, and the same thing we'll wind up doing for Bayes networks. We'll try to learn ourselves how to do inference on Bayes networks without first having to compute the entire joint distribution. Sometimes you can, in the worst case, you may have to compute the entire joint distribution. But for simple queries, you shouldn't have to. That's what the point of Bayes network, Bayes network inference is. Okay. Anyway, for this class, at least the stuff that you've seen, given the Bayes network numbers and the topology, you should be able to see that every entry in the joint distribution can be computed. I showed you that. And once I do that, then you should be you have at least one way of computing every probabilistic query because you have the joint distribution. Okay. And then given a network, you should know how many numbers are needed to be assessed. This is like a corollary. Then finally, networks with special topologies have names such as Markov chain, hidden Markov model, etc. In fact, there's a lot of what you have learned in probabilistic reasoning can become special cases of Bayes networks. Okay, yeah. So this stuff should make sense to you. And then we'll build on that today, and then we'll talk about semantics of Bayes nets and specification of Bayes nets and things like factor algebra, setting the stage up for the next class, and also the reading before next class of doing inference over Bayes networks. Inference over Bayes networks is like theorem proving using rules in logic, as again as theorem proving using truth tables in logic. You understand that? You can always do theorem proving using truth tables. Similarly, you can always do probabilistic reasoning by just computing the entire joint distribution. For discrete case, that is actually feasible. For continuous case, you're screwed because the table is infinitely large for the continuous case. Okay, but for the proof theoretic case in logic, we didn't have to generate the entire truth table. We could compute truth by just applying these rules that we have proved are sound and complete. In the case of Bayes networks, essentially, that is Bayes network inference algorithms. That's the lay of the land. Okay. Any questions? Okay. So for this particular network, this is like a sanity test. How many numbers are needed to specify this network? How many? What? How many? 80? No. Did you answer something? No, you raised your hand.
Oh, sorry, I was just.
Okay. Did anybody have a number? Yes. 16? Okay. That's what he says. Can we double check? Let's do this. So Visit Asia needs one number because it has no parents. That means you just need the probability of that with respect to it. It's what's called the prior probability. Smoking needs one number. Tuberculosis needs two numbers because tuberculosis given Visit Asia, tuberculosis given not Visit Asia, given not Visit Asia. Similarly, lung cancer requires 2, bronchitis requires 2. Okay, this guy requires 4 because it has 2 parents. Okay, and then this guy requires 2, this guy requires 2. Right? So 2 plus 2, 4. What?
To the bottom.
Oh, I'm sorry. This one is, yeah, you're right. There are 2 things. There's 4 here. Right. Because this one, yeah, I don't know what the heck this is. By the way, this is called the Asia network in the Bayes network community. And if they're sounding a little bit racist, that just because you went to Asia, you might be getting tuberculosis. It's not me saying it. I'm from Asia, for crying out loud. So somebody else made it. Okay. But anyway, so that's basically the total number. So 4 plus 2, 6, 6 plus 4, 10, 10 plus 2, 12, plus 2, 14, plus 2, 16, plus 1, 17, plus 1, 18. So there should be 18 numbers. Now, my other question is, if I allow you to change the topology for this network by just removing and adding arrows, for what is the minimum number of probabilities you will ever need for some topology?
The number of nodes.
What? Number of nodes. Because, and how many edges will be there in that case? None. Okay. So 8 will be the 8 for the all independent case. Okay. 8 will be for the all independent case. And then similarly, what's the worst it would be? Yes?
2 to the 8 or 2 to the 9.
1, 2, 3, 4, 5, 6, 7, 8. 2 power 8 minus 1. 2 power 8 is how much? 256. Minus 1, 255. Are people sufficiently impressed now that the number of probabilities can be anywhere between 8 and 255. And 255 also happens to be the size of the joint distribution. You understand what I'm saying? So if you think of 8 variables, it has 256 rows in its joint distribution table. And there are 255 of them are independent. Because if you take any, if you give any 255, you can get the 256th one by adding up the original ones and subtracting from 1. Because the probabilities have to add up to 1. And in the worst case, basis says, that's all I can tell you. In fact, every joint entry is completely, every joint entry is dependent. So in essence, you have to kind of find the numbers for every joint entry separate. Whereas in the 8 case, with 8 numbers, you can explode it into 256 numbers. Because you just multiply those 8 numbers, either those numbers themselves or 1 minus those numbers, to get every entry. You guys are understanding what I'm saying? Ask if you are lost, because things will build on this stuff very quickly. Okay? Yes?
The fewest number of probabilities.
The fewest number. The fewest number basically is there are no arrows at all. So the arrows tell you essentially, so by the way, so the arrows tell you the connections. How are variables dependent on each other? The dependencies here, probabilistic dependencies. It is not causality, it is probabilistic dependencies. What basically a probabilistic dependency says is A and B are dependent if P A given B is not equal to PA. That's it. That's the definition of probabilistic dependence. It has nothing to do with causality. Okay. Okay. And does that answer your question? Any other questions? Okay. Okay. And then so variables, essentially variables, I mean the arrows essentially, the more the arrows, the more the dependencies. The fewer the arrows, the fewer the dependencies. And then we'll actually talk about a formal way of talking about is a set of variables independent of another set of variables given a third set of variables. You see what I'm saying? So so this one is the simplest kind of independence. A and B are independent if P A given B is not equal to P of A. I'm sorry, they're dependent. If it is equal, then they are independent. They're not equal, that means they're dependent. You see what I'm saying? The general idea is the probability that I had coffee this morning. I ask you, what do you think is the probability? You'll see with the number. Then I'll say the probability that I had coffee this morning, given that Joe Biden was wearing a brown shirt. Okay. Or similarly, and then you probably might say, I think it'll be the same. That basically means you think Biden wearing a brown shirt has no impact on me having coffee. On the other hand, I ask the probability that I had coffee, given also that day before yesterday, we forgot to go for groceries. You might say, oh, you don't know, maybe you ran out of coffee. So now that this fact is there, maybe you didn't have coffee at home. So maybe you won't have coffee. Probably there is less chance that you had coffee. You understand what I'm saying? So you are kind of making these connections. They're not causal. They are sort of correlational connections. You see what I'm saying? So this basically, the more independence assumptions you have, the fewer independent probabilities you have to assess. The fewer independence assumptions you have, the more numbers you have to assess. And I made this whole point in the discussion, and I hope you got it, that you should be, there is a Goldilocks world. So if in fact you are in a world where all variables are independent, it's not a good world to live in. Because the data doesn't give you any information of the other variables. You understand what I'm saying? I was saying, for example, so is your grade, and so like things like your grade, your homework performance, your project performance, you are coming to the class performance, etc., etc. These are all independent. Then essentially, given one, you don't know anything about the other. If it is dependent, given one, you have probabilistic expectations on the other. Like for example, I say, oh, this kid basically messed up all their homeworks and never used to show up in the class. What do you think is the probability that they got an A+? You have an expectation, you don't have to say it. The fact that you have an expectation means you think they are connected. That's your theory. And one of the other very important things is that giving the topology of the network is essentially you giving knowledge about the world to the machine. Okay. And for that worlds where you have common sense about, these are worlds about which you understand, you have lived in those worlds. You have connections between, you kind of have expectations between which variables affect which variables. If on the other hand, you are a biologist, okay, I'm a lab biologist, and you're trying to you got a humongous amount of data about different biomarkers and the disease. You have no clue what is causing what. In that case, the probabilistic network itself is learned from the data with no guarantees. That sort of connects to any theory of causation. That's the problem with causality. People don't understand that the fact that you understand what causes what typically is only true for the worlds in which you have some knowledge about. You have no idea about the worlds in which you don't have much knowledge. And that's why that's where you're trying to get the machine to learn. And it doesn't know what causes what. It only knows what is correlated with what. Causality implies correlation. Correlation doesn't imply causality. Do people understand this? You would be surprised how many people don't understand this and how many people make this mistake that correlation doesn't imply causation. Causation does imply correlation, but correlation doesn't imply causation. Yes?
If giving a network of topology is equivalent to feeding it information about the field, does that mean that a topology can be classified in the same way as the environment can? Like that avoids a rule.
No, it's not. I think it's basically your knowledge about how the variables are connected. And it's sort of domain knowledge. And the problem that people don't understand is that from data, you can only learn correlations. You cannot learn causations. In fact, in the example that you guys saw, I said in the RAIN networks, most of the networks are written in such a way that they are consistent with your innate causality that you ascribe to these worlds. If instead of those variable names like that, if I just said A1, A2, A3, A4, A5, A125, you have no clue what causes what in those A variables. All you know is whether or not those variables are conditionally independent. So for example, you may have checked the prior probability of A and the probability of A given that B is true, given the data. If they are different, that means A and B are somehow connected. I don't know how they are connected, they are connected. Is B causing A? I have no idea. Is A causing B? I have no idea. Is A and B causing C? I have no idea. How is this connection occurring? I have no idea. They are connected. And so it's important that, so there is this disconnect between the worlds we understand, where we have a sense of causality, whether it's real causality or fake causality. We did have fake causal theories too. For a while, we had great fake causal theories about how sun is revolving around the earth. Okay, but we do generally have causal theories, and normally the way you can check whether a causal theory is true or not is by these interventions. If you stop the cause, the effect is likely to stop. If you stop the effect, the cause doesn't disappear. You see what I mean? That's why I said in that rain thing, if you dry the grass, rain doesn't stop falling. If you stop the rain, at least that way grass getting wet will be stopped. So the way you have to check this is causality. So you know where this is extremely important, this whole issue of causality? It's important in all probabilistic reasoning. The thing that's extremely important is in this world we are living in right now during pandemic, when we made vaccines. The question is, how do you know that taking the vaccine is the reason this guy was not getting COVID? You understand what I'm saying? And so you go to Facebook and Facebook will have all these conspiracy theories. That's not the reason at all. Nobody knew, nobody really did any experiments. It's actually not, there is no causality at all. It turns out, for example, what's called RCTs, randomized control trials, is a hard way of establishing causation. It's a beautiful but hard way of establishing causation, randomized control trials. And that's basically the only way you can. So in some sense, you almost have to completely do randomized control trials. So even if you really believe that this vaccine works, you should not give it to some people. Ethically, maybe you will feel bad that if you really believe that this is working, you should be giving it to everybody. Some of those people who are not given it are going to get COVID. But there's no way you can establish causation without doing that kind of an intervention, causal intervention. For some people, we gave fake vaccine, basically water, placebo. For some people, we gave the real vaccine, which we think is supposed to improve the likelihood of you getting COVID. But correlation is not causation, and you want to establish that there is a causation. And randomized control trials are a cheap way, is a pretty inefficient way, really, of establishing causation. But that's the only thing you can do if you don't know what causes what, even in the intermediate levels. Yes, there was a question. Yes.
So I don't know. This made me think of how like does this also cause like the concept of superstition in like neural networks, that it just assumes that if you clap your hands at certain times, certain things happen?
No, basically all machine learning, every piece of machine learning you have learned until now, and will learn further, is all correlation. Correlation sometimes implies causation, sometimes it doesn't. And figuring out what is correlation versus what is causation is what civilization was. You understand what I'm saying? We kind of knew, even when we were bozo, old, and ancient people, they knew that seems to be that in the morning sun is on one side, in the evening sun is on the other side. That's an observational evidence. The question is, what is causing it? Is the sun going around Earth or Earth going around sun? The most obvious thing is sun must be going around Earth, because I'm standing here and the guy is going around like this. So that's it. I'll go with that. Yes.
Might be a kind of bad question, but when you say getting topology from data, like with just 8 nodes, aren't there a huge amount of possible like?
Yeah, yes, yes, yes. And furthermore, since you asked, I would say that basically in those cases, you will wind up doing some sort of a local search over topologies. I mean, start with the topology and try to make changes to it. And typically you try to make changes to it. Again, I'm jumping 2 classes ahead. But so that will you'll remember this when I get there, that we make changes to the topology. So if you're given 2 networks, which network is better in explaining the data? So there is a way of computing the likelihood of the data given the networks. So the expectation is that the network that increases the likelihood of the real data is the real network. Okay. However, that's sort of like basically saying, that, let me see. Well, I can't. So basically, think about this. These are all connected. Those are points. Okay. I actually maybe I'll give it slightly different points. Okay. So there is one hypothesis. There is another hypothesis. Which one is better? The one which makes the data more likely. The thing that goes through all the training data makes the data more likely. But even as I said this, you already knew that by increasing the complexity of the function, by making it a much higher order polynomial, I can make all the data more likely. You understand that? This is what we said, that an best 8th order polynomial that goes through the data cannot have higher training error than the best 3rd order polynomial. It can at most have the same amount error, oftentimes much less error. And we knew that going through every little data point can be overfitting. Coming back to your answer, what happens in the Bayes networks is there is a topology. There is another topology. Right? Which one is better? You will basically, you have a data set, you will compute the probability of data given network. And whichever is higher, you say that is the better network. Just like computing the error for the training data in this other case. Except the problem with that is if you add extra edges in a network, that is like increasing the expressiveness of a polynomial by going to the higher degree. Is what I'm saying? Which means if you are not careful, and if you only care about data likelihood, the best topology is always the complete topology. That means complete acyclic graph. Do you understand what I'm saying? Right? And so what did we do to stop that from happening in the other case? We would put regularization terms, saying subject to the degree of the polynomial being less than something. You can do the same thing for the network topologies too. Learn the topology subject to not only the data likelihood plus the complexity of the network itself. The complexity is measured in terms of the number of edges. That's your regularization term. But we jumped like 2 classes. We'll come back to it when we get there. Okay. Okay. Any other questions on this stuff? Okay. So you saw this network. And people understood this, how P cloudy, not sprinkler, rain, not wet grass was computed from these numbers. Anybody not understanding? Anybody had questions about that? You should know this. This is the minimum, because this ultimately is one entry in the joint distribution table. If you know how to compute that entry, you can compute the rest of the 16 entries. Once you have the joint distribution, you can answer any question. Okay, I'm just going to double check by just saying that, the way cloudy, not sprinkler, rain, not wet grass occurs is I'll start in the topological order. The cloudy is positive, true, so that means it's 0.5. I'm just writing the whatever is here. And then sprinkler has to be false given cloudy is true. Sprinkler false given cloudy is true. Cloudy is true is this row. And if cloudy is true, sprinkler true is 0.10. Sorry, what did we say here? What should I do here? Okay, yeah, 0.10. So sprinkler false given cloudy is equal to true is 1 minus 0.10. That's why 1 minus 0.1. And then similarly, you need rain given not sprinkler and cloudy. But according to this, basically rain depends on cloudy. So basically cloudy is true. And when cloudy is true, rain would be 0.8. And then finally, not wet grass given sprinkler and rain. Not wet grass given sprinkler and rain. And that would be wet grass given sprinkler and rain, which is, I said, not wet grass given sprinkler, not sprinkler and rain. Not sprinkler and rain. So not sprinkler and rain is this row, for which wet grass will be 0.9, not wet grass will be 1 minus 0.9. You multiply those numbers, you'll get that entry. Similarly, you can get the other 16 entries. And since I've been saying that if I know, I'll come back to this in a bit. I just want to make sure that we're on the same page by saying, you really, really understand that if you have the joint distribution, you can compute any probabilities. Because this is my 0th order, truth table based way of dealing with probabilities, right? Because I'll give you a network, you will convert the network into the joint distribution. And then you should be able to answer any query. So the question is, what kinds of questions can I ask? This is basically toothache and cavity. Which, by the way, I have taught this like millions of times, and I never had teeth problems, except this year. So this is like special this year. I actually understand what it means to have toothache. I never had toothache before. But anyway, so it's no longer just an abstract issue. So toothache, does toothache cause cavity or cavity cause toothache? We don't know, we don't care. But the joint distribution requires cavity toothache, cavity not toothache, not cavity toothache, not cavity not toothache. Those would be the 4 rows. And I put those 4 rows numbers like this. If I do this, then you should be able to answer any of these queries. And there are no more queries you won't ever answer. So CA and TA, you just read it up from the net. Okay. CA itself, for CA itself, you essentially consider all the places where CA is true, irrespective of what TA is, and add up those probabilities. So that will be 0.04 plus 0.06. This idea is called marginalization. There are all these names for this. You're marginalizing the other variable. So in general, in a n variable joint distribution, the easiest probabilities you can get just by lookup is the joint distribution entries. Anything else, you have to marginalize, because The other variables values don't matter. So whether they're true or false, you add up those possibilities. Here, normally in the marginalization case, you sum over all the other values of TA. That's what you did to get CA. To get the marginal probability of CA, you considered, so basically you just wrote like this. PCA is nothing but sum over TA, PCA, TA being true, false, PCA, TA. So let the TA vary to be true and false and add up those numbers. The interesting thing is, if this were continuous probabilities, continuous variables, the summation would be integration, which leads to a nerdy joke, which says that Bayesians are the only people who feel marginalized when they are integrated. Understand what I'm saying? This kind of a joke grows very well in your parties. So you should use that. Okay. Okay. So basically, by integrating, you are marginalizing the other variables. Integration is the sum in our case, for discrete case. Okay, what about PTA? It's the same thing. You keep the TA constant and add up the numbers. So it's 0.04 plus 0.01. What about CA-RTA? This is the whole thing. That textbook makes all this great argument about why this particular way, in fact, the way this has been defined is PCA plus PTA minus PCA and TA. It kind of makes sense. It looks from a Venn diagram case, but it turns out that it's one of those things which is axiomatically taken. And the only semantic reason is this definitis argument that if you do not believe this rule, then Definity can set up a Las Vegas gamble where he will get all your money. You understand what I'm saying? So that's a beautiful way of saying why math matters. So if you don't believe this rule, if you want to have a different rule, then Las Vegas you can lose because they can set up a particular gamble, which basically exploits this inconsistent belief you have. So here a PCA-TA blah, blah, blah is point. This is equal to 0.1, right? 0.04 plus 0.06 is 0.1. So this will be equal to 0.1 plus this is 0.5, 0.05 rather, 0.05, sorry. Minus PCA-TA, CA-TA is 0.04. That basically would make it 0.11, right? Okay. And then the other most interesting thing is PCA given not TA. That is the conditional probability. It's actually conditional probabilities are the most important things. And so the way you always define this is PCA and not TA by P not TA. PCA and not TA, CA and not TA, 0.06. By P not TA, we know TA is 0.05. Not TA is 1 minus 0.05. That's 0.95. You see, I calculated any. You can make up any probabilistic query in terms of these two variables, and I can answer it for you because I have the joint distribution. This is what I mean, that if you have joint distribution, you can answer every probabilistic query. Similarly, if you have the entire truth table, you can check model theoretic entailment. It's a costly way to do it, but it's possible. That's the semantics, ultimately. And everything else has to be essentially justified in terms of this way of computation. It's the costly way of computation, but if you can once prove that the shortcut you're doing would be correct with respect to this, then you can always use the shortcut. That's what we did for logic 2. Okay. Any questions on this stuff? This is basically what we mean by saying joint distribution allows you to answer all queries. Okay. One other thing that I want to say. So in general, this is worthwhile to say too, that in general, this is the other thing that I was saying last class, that probabilistic reasoning is inherently non-monotonic. If you sort of think of non-monotonicity as probability can go both up and down as the evidence increases. As more and more other variables values are given, then the probability can go up and down. So that's what happened in the Tweety example. Prior probability that a bird can fly, some number. Prior probability that, Tweety, given that Tweety is a bird, Tweety can fly, some number. Given that Tweety is an ostrich, Tweety can fly is a smaller number. Given that Tweety is an ostrich which is magical, Tweety can fly, is a bigger number again. So the probability keeps changing. And in general, the most useful probabilistic reasoning involves computing posterior distributions. Posterior means after the evidence. So like basically, let's say this is probability, prior probability of a distribution. We normally think of distributions. It's better to think in terms of distributions rather than the single values. So distribution of A is if the A can take values between this to this, then the prior probability distribution of A is that it can take each of its values with the same probability. So all those probabilities should add up to 1. When I give some evidence, probability A, given that B equal to true, the distribution of A might change. It might become like this. So now A is more likely to take values in this region than in this region. Before it could take values anywhere. So this is what happens when you, in probabilistically speaking, when you get more evidence, your distribution hopefully gets sharper. As it gets sharper, you know what is the actual value. Hopefully. But sometimes it actually can flatten the distribution too. Okay. So this would be the kind of thing you really hope. PA given B equal to true, C equal to false, it says A will be most likely just in this region. So if you're a doctor and A is the disease, you're trying to decide whether the disease status is true or false or some number in between. How many tests are you supposed to do on the patient? Upfront, basically, since it can be either true or false with equal likelihood, you probably need to do some tests. After the first test, you got this yellow distribution. After the second test, you got the blue distribution. And you might decide to stop there. Or if you're a doctor who basically is trying to maximize not improving the patient's health, but reducing the chance that the patient will sue you, you will just keep doing tests. More and more tests to kind of try get the distribution as peaked as possible. Okay, so that's the thing about in Bayesian reasoning. In probabilistic reasoning, you're all interested in computing, not, there is no point in talking about what is the value, what is the class of the picture. You want to say, originally, in the ImageNet case, originally there were 1,000 classes and 14 million examples. Imagine you could have computed the prior probabilities for all the classes. That means how many dogs were there in the ImageNet of 14 million? How many cats were there? How many dogs of this type are there? How many dogs of that type are there? So for each of the 1,000 classes, you computed the frequencies. That would be the prior probability that a picture belongs to a certain class. You understand what I'm saying? And in fact, it turns out that in ImageNet, most of the things are dogs. And the next biggest is the cats. So you are less likely to go wrong by saying everything is a dog or a cat. Way more likely to go wrong by saying something is a tank, because there are much fewer tanks in the data to begin with. Then what the neural network is doing, especially with the logistic, final layer, is it is computing the posterior of the class given the inputs. That basically is changing. This class is more likely, this class is less likely. Do you understand what I'm saying? We did this, right? That's what we were doing. We were computing the probabilities at the end. Those probabilities better be different from the prior probabilities, because prior probabilities anybody could have said beforehand. These are distribution probabilities having seen the pixels. Pixels is the evidence. Okay, and all probabilistic reasoning is computing posterior distributions, which leads to the second joke, which is ye shall know your Bayesians by their posteriors. Bayesians are into computing posteriors. There is no such thing as what is the value. It is how did the probability distribution change over the values. It will be very, very unlikely that after some amount of tests, the distribution becomes like this. That means it's basically all probability mass is exactly at one class. That's very unlikely. Instead, it is the distribution becomes peaked. In fact, the idea called entropy of a distribution captures that. Entropy of a distribution captures that. And the uniform distribution has the highest entropy, whereas a peaked distributions have lower entropies. And a distribution which actually puts all its probability mass on a single value has the lowest entropy, because there is no mystery left at that point. And all of this discussion we made with respect to discrete distributions. The interesting question is, what is the distribution for continuous variables from -infinity to +infinity continuous variables that has the maximum entropy? Yes.
Normal distribution.
Exactly. That is the way to think of normal distribution. Normal distribution is essentially the uniform distribution for continuous -infinity to +infinity case. And then you can get the normal distribution to peak by reducing, its variance. Okay, that's that. One other thing that I want to mention before we go forward is we talk a lot about Bayes rule. Bayes rule is basically converting conditional probabilities from one form to other. So for example, P, I should probably use a different color. Yeah. PA given B is PA and B by PB. So that means PA and B is PA given B times PB. Similarly, PP given A is PA and B by PA. You can write it PB and A, but B and A is the same as A and B. So that basically means A and B has a new expression, B given A times PA. And since these two have the same left-hand side, the right-hand side must be equal. So that basically means PAB, PA given B times PB is the same as PB given A times PA. Right? If I do that, then I get a way of computing PA given B in terms of PB given A. This looks like, this is Bayes' rule, the famous, really famous Bayes. And the question is, why did Bayes become that damn famous for doing this very simple, basically equating two different expressions for A and B? The reason it is very useful is that in many real world scenarios, one of them might be cause and other of them might be the symptom. And I think I mentioned this in a previous class, that if you're thinking in terms of P disease given symptom, which is what you go to the doctor for, and the doctor then can compute that in terms of symptom given disease times P disease by P symptom. That's why Bayes rule is useful. Okay? That's what that particular slide is saying. The second thing, and this is an important thing to keep in mind, basically, in looking at, when we go forward, when looking at Bayes network inference methods, people do this thing called normalization trick. That's what this normalization trick is. And what it's saying is that, remember, P disease given symptom is P symptom given disease by P disease times P disease by P symptom. This, you could get, because textbooks will tell you how to get this. P disease, prior probability of disease, you can also get that. It's much harder to get P symptom. In general, another way of thinking is that P query given evidence is computed as P evidence given query times P query by P evidence. Computing the probability of the evidence is painful. So it turns out that if you don't feel like assessing that probability, I can give you a shortcut, which is anyway, you are computing PD given S. Suppose you also compute, and then you write the PD given S, you think of 1 by P of S as alpha. Let's just assume 1 by P of S is alpha. Then PD given S is alpha times PSD, PS given D times PD. I say, why don't you also go ahead and compute P not D given S? Okay, that would be, again, have the same PS in the denominator, but the numerator will be different. So it will be again alpha times PS given not D times P not D. Okay, now if you can do this, then if you add up both the left hand side, it has to be equal to 1, which means you can actually compute alpha. You understand what I'm saying? So people, since they know that they can do this, they will say, we will using normalization trick. And you might be left scratching your head as to what the heck is going on. What is going on is this. If you just wanted PD given S, you have to also get P, the probability of the symptoms. But if you hate computing the probability of symptoms, then you go ahead and compute P not D given S2. In general, since D is a Boolean variable, by computing both P D given S and P not D given S, we computed conditional distribution of D given the symptom. You see what I'm saying? We computed a conditional distribution of D given the symptom. So instead of computing just the conditional probability of a particular value for the variable given the evidence, if you compute the distribution, which is really what you should be doing according to what I was telling you. If you think of Bayesian inference as computing posteriors, then you will always be using this alpha trick, the normalization trick. Do you guys get that? Okay. So again, this is not a big deal, but people kind of, you assume that you know it, and so I'm just pointing this out. So now a few other things before we get done today, which is that the conditional probability actually is very useful in computing any joint entry. Any joint distribution entries will be conjunctive entries. Right? So one of the advantages is if you have P A and B, you can write it as P A given B times PB. So if you have P, A, B, C, it can be written as P, A given BC times P, B given C times BC. See what I'm saying? In general, if you have entry x probability of x1 to xn, it can be written as probability of x1 to xn can be written as basically you have to read the other way around. So xn given x1 to xn minus 1, xn minus given, xn minus 1 given the previous, and so on, all the way to the front. So that's the chain rule. Okay. So the chain rule essentially just becomes, can be written this way. You understand this? In writing the chain rule, it turns out the order doesn't matter because A and B and C and D is the same as B and C and A and D is the same as A and D and B and C, etc. Blah, blah, blah. And you can apply the chain rule in each way, and they're all correct as long as you have those probabilities. Why am I making such a big deal about it? It turns out that you were using the chain rule along with this idea that a node is conditionally independent of its ancestors given its immediate parents to compute those numbers, those probability numbers in the Bayes network. Do you understand what I just said? In particular, this is what you're doing. Suppose you're trying to compute in the burglary, earthquake, alarm, John calls, Mary calls example. You're trying to compute the entry, John calls and Mary calls and alarm and not burglary or not earthquake. That would be one of the entries because you have given the values for each of the variables. So there should be an entry in the joint distribution for that. You want to compute this. What I will basically say is write the chain rule in the anti-topological sort. That means basically, the fact this is written that way: John, Mary, A, not B, not E. John and Mary will come first, then alarm will come, and burglary and earthquake will come. If you go opposite to the topological sort. Do you guys remember topological sort? Right? If you write it in the negative inverse topological sort, then the advantage is you will always be asking the conditional probabilities of a variable given its parents and other stuff. And the advantage is that the parents essentially shield you from the ancestors. Parents essentially shield you from the ancestors. Okay, so that's basically what happened. So John given Mary, alarm, not burglary, not earthquake, okay, is the same as, actually, in fact, it's not just ancestors. The right thing is a node is shielded from all its non-descendants given its parents. Siblings are also non-descendants. You see what I'm saying? Right? If you understand that, that's basically what is captured by the Bayes network. And if you use that, then John given Mary, alarm, not B, not E, is the moment alarm is there, Mary doesn't matter because it's a descendant. Burglary doesn't matter because it's an ancestor. Earthquake doesn't matter because it's an ancestor. So P John given Mary, alarm, not burglary, not earthquake is nothing but P John given A. You see what I'm saying? This line is correct irrespective of the configuration of the network. This line is correct only because the configuration of the network is such that alarm is an immediate parent of John calls. Okay. Once you do that, then similarly M A not B E will be M A. And then similarly A given not B E will be still A given not B E because A does have two parents. And then P not B and P not E. Okay. And so actually P not B given not E is the same as P not B. That is another thing you have to see, because burglary is independent of non-descendants given its parents, and it is parentless. So not B given not E is the same as not B. You guys get this? Okay. So you did this. I mean, this is what we did in that sprinkler example. But this is the semantic reason why you are allowed to do it. You are essentially combining the chain rule, which everybody is allowed to use. It's just basically part of probability theory, with conditional independence that is included in this particular Bayes network. And you did this by essentially writing the conjunction in the anti-topological software. This is the proof, quote unquote, that what you're doing is not gobbledygook. Okay. So since you can get this, you can get every other joint distribution entry. And because you have all the joint distribution entries, you can compute any random other query given, for example, what is the probability John calls given Mary calls? That's hard, but you need for that. So if you want to do this, you can't just look up the table. So really, this is nothing but P John and Mary by P Mary. The John and Mary would be John and Mary being true with all other variables taking any other value and summing those probabilities. Because there are 32 entries. There are 32 entries, right? Of which how many will have John and Mary true? 8 of them. Because the 2 variables have been given values, the other variables can change. So there are 8 configurations for the other variables. You add up those 8 rows, you will get the John and Mary. And P Mary, you have to add up 16 rows where Mary is true. But look, you did Bayes network inference. The rest of how to make inference faster is, can you avoid essentially doing this in this brute force way of actually first computing the joint distribution. In particular, you can, for example, see, suppose I asked, what is the John calls given alarm? Please actually pay attention. This is a cute example that I just thought about. What is the John calls given a alarm? You can do it the hard way, which basically is P John and alarm by P alarm. That would be sum of 8 rows by sum of 16 rows. But it is also here. It's also here. Why did you waste your time doing that the hard way? In fact, if you do it the hard way as well as the easy way, those numbers should be the same. If not, math has fallen apart. And since math will never fall apart, you shouldn't have to do this the hard way. Some probabilities can be computed without doing this hard way. Some probably you have to do the whole hard way. And the computational efficiency is figuring out exactly how much work you have to do, just only do that much. Do you understand what I just said? And the equivalent of this exists in logic 2. Equivalent of this exists in logic 2. Let me show you that. Yeah, equivalent of this exists logic 2 because Suppose I have A1 to A1000 as the Boolean variables. Okay, and my knowledge base says A75 implies A347 and A75 is true. Given this knowledge base, I want to check, given this knowledge base, I want to check if A347 is true, isn't it? If you did it in the truth table way, you write a 2 power 1000 table. 2 power 1000 table. Compute all, check all the rows where knowledge base is true. Make sure that in all those rows, A347 is true. And I say, yay, I did it. But if you actually figured out proof theory and you know that modus ponens rule works because you proved it works with respect to model theory already once, you just use the shortcut. Do you understand what I'm saying? Okay. At one time, I used to say that the model theory versus proof theory is, strangely enough, it's part of life is full of crazy analogies as far as I'm concerned, is strangely enough like conventional oven versus microwave oven. You didn't expect this, right? Conventional oven versus microwave oven for baking potatoes. Okay. If you want to bake like 8 potatoes or 1 potato, conventional oven more or less takes the same amount of time. First needs to heat up the entire oven, which is like a room-sized oven, and then it will then heat up the potato. For 1 potato, it's much better to use microwave oven. But then if you're kind of doing 8 potatoes in the microwave oven, it takes almost 8 times the time. At some point of time, it might as well be used. You may as well just use the conventional oven. Okay, the truth table way basically charges the same cost for every theorem. The proof theoretic way charges different costs, computational costs for different theorems, depending on which are easier to make. Okay, fine. So, and then it's very important, I mentioned this arrow direction is not equal to causality. It's like one of those things, like where I said, remember uniform cost search has non-uniform edge costs. And you say, why the heck did you make that name raw? And I say, I didn't make the name. I just tell you the name that everybody agreed on, right? And Bayes nets put arrows, and every junior thinks arrow means causes. There is no causality like at all. It's not built into the semantics. However, if you are making the network, you're more likely to make it in the causal direction. And one of the interesting things is that if you know the domain, and if you make the network in the causal direction, you will wind up having fewer edges, heuristically. To say that point, actually, I would get out of this, and I'll show you this later part and then end today. Yeah, which is if I'm asking experts, if you basically are asking, Bayes networks became very famous. The last time around AI was huge in 1980s when they had these medical expert systems. And the medical expert systems, is exactly what, the symptoms given diseases. Typically, diseases cause syndromes, syndromes cause some other things finally cause symptoms. And people, the doctors have an idea of this. And so what they would do is they'll ask the doctor, among these variables, I will present these variables to you and say, when I introduce a new variable, can you tell me what are all the variables that we have seen until now? It depends on, that means it's only correlated. It's not caused, but correlated. And the order in which you present the variables if you happen to have presented the variables in approximately causal order, then there would be the least number of edges. So quickly, here is what I would show for the Mary calling, John calling, alarm, burglary, and earthquake. Use you as the experts. You understand Perl world. So I basically introduce Mary calling, obviously the first variable. Then I put John calling, and I say, would, as of now, would Mary calling be connected to John calling? And if you say no, that means basically John calling given Mary calling, would that be different from John calling, given just at this point that these two variables are there? And to the extent you would say no, you won't put an H. If you say yes, you have to put an H. But given the world that you are in, actually, if Mary calls, John is more likely to call, because probably Mary called because of the burglary, and so John also would have felt the burglary, seen the burglary and alarm going off, and so you would have. So you would actually say, yeah. If you are ordering it that way, Mary calling, John calling, Mary calling will affect John calling. So I'll put an H. Notice that had I asked you earthquake and burglary, and I say just earthquake occurred, now burglary is occurring. Would burglary occurring depend on the earthquake occurring? You would say no. Although in Manhattan, when power went away, burglaries increased. So actually, there's a connection there. Maybe the other way around, I say burglary occurred, will the earthquake occur? That at least, if you don't believe in some vengeful God who makes earthquakes to punish the burglars and also punishes everybody else whose houses are in the earthquake region, if burglary occurred first and then I introduce earthquake, you will say, no, it's not connected. Then you won't put a link. So then I will introduce alarm, and then I'll say, is alarm connected to any of them? The reality is they're both connected to alarm. So I have to put those two links. Then I put burglary, and then I say, is burglary connected to any of the previous three? And basically, well, alarm. And then similarly, earthquake. Earthquake, essentially, alarm, of course, is connected, but so is burglary connected. Because you don't need both burglary and earthquake for the alarm to go. So this is your expert qualitative decision. If you did this, you would have gotten this network. And this network, compared to this other network, which presents the variables in the causal order, where you know the causation. Remember, if you're asking the expert, if you don't know the causation, then you may very well likely ask it in this direction. And then if you, how many probabilities are needed for this? 13 for this, you should be able to see that this is 13 and this is 10. And in the worst case, you will get that network. That will be 31. Okay, so we'll stop here. But essentially, this tells you how, if you know the domain, if some expert knows what causes what, you can make the network right, network topology by asking them a series of questions. Sorry.